Alright, hello everyone. This video is going over the Chapter 12 test review. The first question says, what volume will 1 mole of a gas occupy under standard temperature and pressure? Well, we know under Avogadro's principle that under standard temperature and pressure, remember standard temperature is 273 Kelvin and standard pressure is 1 atm. Under those conditions, 1 mole of a gas is equal to 22.4 liters. Number 2 says, what variable is mentioned in the ideal gas law that is assumed to be constant in the other gas laws? Well, in the ideal gas law, we have PV equals nRT. Well, we know R is a gas constant, so that is always constant, so that will not be the answer. And then we know in our other laws, we have pressure, volume, and temperature. We do not, however, have N or number of moles in our other gas law. So N or number of moles would be the answer for number 2. All right, number 3 says a certain mass of gas in a 2.25 liter container has a pressure of 164 kPa. What will the new pressure be if the volume of the container is reduced to 1.5 liters and the temperature stays constant? So you can see in the first sentence we have that blue 2.25 liters, that is V1. Then we have 164 kPa in red, that is P1. It's asking for the new pressure, so we're going to be solving for P2 and it gives us the final volume. So if we have a P1V1 and a P2V2, we are going to be using Boyle's law, which is P1V1 equals P2V2. Now, if we're solving for P2, we need to divide V2 on both sides. So our formula will be P2 equals P1V1 over V2. Now that we have that, we can go ahead and plug in all of our units. So our initial pressure is 164 kPa. Our initial volume is 2.25 liters. And our final volume is 1.5 liters. So as you can see, our liters unit cancels out and we're left with kPa. Then in our calculator, we would do 164 times 2.25 divided by 1.5, and you get 246 kPa, and that would be your answer. Alright, number 4 says a 50 milliliter sample of gas is cooled from 119 degrees Celsius. Let's go ahead and bring that to Kelvin. 273 will give us 392. Then we have 80 plus 273, which will give us 281. If the pressure remains constant, all that means is that pressure does not apply. So we are not considering pressure in any of this math. What is the final volume? So we are given a V1 and a T1. We're solving for V2, and we're given a T2. So with V and T, or volume and temperature, we're going to be using Charles' law. Charles' law is V1 over T1 equals V2 over T2. Now, if we are solving for V2, remember the cross multiplication that does not involve the variable is going to be on top. So we're going to have V1, T2, and everything else will be in the bottom, so T1. And now we can go ahead and plug in those values. So V1 is 50 milliliters, T2 is 281 Kelvin, and T1 is 392 Kelvin. So if Kelvin cancels out, we do 50 times 281 divided by 392. That will give us 45.0 milliliters, and that is our answer. All right, number 5, if the gas pressure in an aerosol can is 148.5 kPa at 23 degrees Celsius, So let's add 273 to that. What is the pressure inside the can if heated to 298 degrees Celsius? So we are given an initial pressure. We are asking for the new pressure, so we're going to be solving for P2. Then we're giving an initial temperature and a final temperature. So if we're using pressure and temperature, we're going to be using Gay-Lussac's law, which is P1 over T1 equals P2 over T2. So we're solving for P2. So the cross multiplication that does not involve your variable is going to be in the numerator, and everything else will be in the denominator. Sorry, I accidentally wrote 2, I meant to write 1. So now we will plug that in. So P1 is 148.5 kPa. T2 is 571 Kelvin. And T1 is 296 Kelvin. Kelvin cancels out. You're left with kPa as your unit. If you do 148.5 times 571 divided by 296, you get 286 kPa, which is your answer. A steel cylinder is filled with a gas at a temperature of 25 degrees Celsius. If we add 273 to that number, we get 298. And a pressure of 225 kPa. What will the pressure be? So we're solving for P2 if the temperature is raised to 47 degrees Celsius. So we have a T1 and a T2, and we have a P1, so we're solving for P2. If we have pressure and temperature, that's going to be Gay-Lussac's law. P1 over T1 equals P2 over T2. We're solving for P2. So again, the cross multiplication that does not involve the variable will be on the numerator. Everything else will be in the denominator. So now we're going to solve. 225 kPa is your initial pressure. 320 Kelvin is your final temperature. And 298 Kelvin is your initial temperature. So Kelvins cancel out, you're left with kPa. 225 times 320 divided by 298 will give you 242 kPa, which is your answer. Okay, so in question number 7, it says what volume, so we are solving for volume here, is occupied by 0.58 moles, so that is your N, of gas at 98.4 kPa, which is pressure, and 11 degrees Celsius, which when added to 273 would be 284 Kelvin, and that is your temperature. So since we have a P, a T, an N, and we're solving for V, this is going to be using the ideal gas law. Now, if we are solving for volume, we need to divide the pressure. So it's going to be nRT divided by P. Now our N is already given to us at 0.58 moles. Our R value depends on the pressure. So since we have kPa as our pressure, we will be using 8.314 liters times kPa over moles times Kelvin. Our temperature we found to be 284 Kelvin, and our pressure is 98.4 kPa. Now if we look at our units, moles and Kelvin both cancel out, and kPa cancel out, and you're left with liters. If you do 0.58 times 8.314 times 284 divided by 98.4, you would get 13.9, and that would be your answer. A gas occupies 2 liters at SDP. What volume will the gas occupy if the pressure is increased to 2 atm? So it's telling that you have an original volume and you have standard temperature and pressure. So later in the question, it says temperature is kept constant, so you kind of ignore this standard temperature. However, we do know that we have an initial volume of 2 liters and an initial pressure of 1 atm, since our other pressure is in atm. So then it's asking for the new volume, or V2, when the pressure increased to 2 atm. So we have P and V, which would be Boyle's law. P1 V1 equals P2 V2. We are solving for V2. So if we divide P2 on both sides, we'll get V2 by itself. So we'll get P1 V1 over P2. And now we plug in. Our initial pressure, since our final pressure is in atm, standard pressure will be P1, and that is 1 atm. Our initial volume is 2 liters, and our final pressure is 2 atm. So atm cancels out, we're left with liters, and everything cancels out, you're left with 1 liter. All right, number 9 says a sample of gas is held at 10-liter volume at 175 kPa. The temperature is kept constant. Remember, whenever it says this, that just means it doesn't matter in this specific equation. So temperature is not going to change anything, so you can kind of just leave it alone. And then it says the volume is decreased until the pressure is 350 kPa. So we're given 2 pressures, we're given a volume, and we're asking for the new volume. So that would be pressure and volume again, which is Boyle's law, P1 V1 equals P2 V2. So now, since we know that we're solving for the new volume, we're going to make our new equation by dividing P2. So we have P1 V1 divided by P2, and now you plug it in. So pressure 1 is 175 kPa, volume 1 is 10 liters, and our final pressure is 350 kPa. So kPa is going to be canceling out, we're going to be left with liters. 175 times 10 divided by 350 is going to give you 5 liters, and that would be your answer. So the molar volume of a gas is defined as the volume that 1 mole occupies at STP, which is going to be 22.4 liters. And the ideal gas law, the units of R are going to change based on the different units of pressure. So remember, there's 2 that you had to memorize for this test. It was the R value for atm and the R value for kPa. Now remember, both of these are units of pressure. So if you are given or you're trying to solve for atmospheres or atm, you're going to be using the R value 0.0821 liters times atmospheres over moles times Kelvin. Now the reason you use this one is because you either want to end up with atm or cancel out atm. So atm has to be in that unit. Now same concept goes for kPa. If you are given pressure in kPa or you're trying to solve for pressure in kPa, you're going to be using 8.314 liters times kilopascals over moles times Kelvin. That way, kPa can either cancel out or be left over. So as you can see, volume is the same unit, liters, N is the same unit, moles, and T is the same unit, Kelvin. The only thing that's changing here is the pressure units, which is atm and kPa. So determine the Celsius temperature of 1.5 moles of ammonia contained in a 10-liter vessel under a pressure of 2 atm. So as you can see, I kind of color coordinate these. You can see that all of them are different colors. So we don't have an initial and a final, we just have one of each. Now we also have moles. All of those signs are telling you that we're going to be using the ideal gas law, which is PV equals nRT. Now it says determine the Celsius temperature. However, right now we're just going to focus on solving for T, which is actually in Kelvin. And then once we get our Kelvin, we can go ahead and subtract 273 in order to get our degrees Celsius. So in order to solve for T, we're going to have to divide by NR. So it's going to be T equals PV over NR. Our pressure unit is 2 atm. Our volume is 10 liters. Our number of moles is 1.5. And since we are given pressure in atm, we're going to be using the R value 0.0821 liters times atmospheres over moles times Kelvin. Liters and atmospheres cancels out, moles cancels out. We're left with Kelvin as our unit. We're going to take 20, which is 10 times 2, divided by 1.5. Sorry about my dog snoring. And then we're going to divide it by 0.0821. That will give us 162.4. We're going to subtract 273 from that. And we get negative 110.6, which will round to negative 111 degrees Celsius. Then number 13 says, what volume of oxygen gas is needed for the complete combustion of 40 liters of hydrogen gas? So it's basically saying that you are given a balanced chemical equation. If you have 40 liters of hydrogen, how much oxygen would you have? Now, since hydrogen has a coefficient of 2, it means it will have double the amount of oxygen. So if we have 40 liters of hydrogen gas, we will have 20 liters of oxygen gas. Which of the following states that equal volumes of gases at the same temperature and pressure contain the same number of particles? That is going to be Avogadro's principle. Number 15, a 0.5 liter container of nitrogen gas at 18 degrees Celsius is heated under constant pressure to the boiling point of water. What is the new volume? So you're given two temperatures, you're given one volume, and you're asking for the new volume. So we're solving here for V2, and we have volume and temperature, which is going to be Charles' law, V1 over T1 equals V2 over T2. Since we're solving for V2, our new equation will be V2 equals V1 T2 over T1. Now, before we do any of this, we're going to have to change our degrees Celsius to Kelvin. So if we have 18 plus 273, that's going to give us 291 Kelvin. And this one would give us 373 Kelvin. So if we're looking at V1, that will be 0.5 liters. T2 will be 373 Kelvin. And T1 will be 291 Kelvin. So Kelvin cancels out, we're left with liters. All we do is 373 times 0.5 divided by 291, and you get 0.641 liters. Alright, what happens to the volume of the gas if the temperature is increased? So volume and temperature is going to be Charles' law, which is V1 T1 equals V2 T2. Charles' law and Gay-Lussac's law, the variables are directly related, meaning that as one increases, the other one will also increase. The reason being is because when you have fractions, say you're starting off with a value of 2 for V1 and a value of 2 for T1. If you increase your volume to, let's say, 4, that means you also have to increase your temperature to 4, because remember, they have to equal each other out. So that is why they are directly related. So number 18, the gas law shows a relationship between volume and temperature. We just went over that. That is Charles' law. If solving for the pressure in the ideal gas law, what would your equation be? So we have PV equals nRT is the ideal gas law. If we're solving for pressure, we would then have to divide V, so it'd be nRT over V. Number 20, what pressure would be exerted in 76 grams of fluorine gas in a 1.5 liter vessel at negative 37 degrees Celsius? So first let's get that to Kelvin by adding 273, so that will give us 236 Kelvin. Then we have grams when it's supposed to be in moles. So we can take fluorine, which is 18.998 times 2, because fluorine is diatomic. So we can take 76 grams of F2 and convert it to moles using the molar mass. So if I take 76 divided by 37.996, that will give us 2 moles of F2. So this number right here is 2 moles. So now that we have everything in order, we can go ahead and solve for pressure. So if we have PV equals nRT, we're going to divide V over to get P by itself, so it'd be nRT over V. N is number of moles, which is 2. Since it says in ATM, we're going to put our R value of 0.0821 liters times atmospheres over moles times Kelvin. Temperature is 236 Kelvin, and on the bottom is volume, which is 1.5 liters. So if we look at units, liters cancels out, moles and Kelvin cancels out, we're left with ATM as our unit. Then if we do 2 times 0.0821 times 236 divided by 1.5, you will get 26 ATM as your answer. So on this last slide, it's basically just asking you which log you would use for each situation. In 21, you can see that we're given moles. You're given the moles for each individual gas. However, at the end, it's asking you about the mixture of the gases. So your N value here would actually be 8 moles because you're adding them together. Then you're given a volume, a temperature, and asking for pressure. So if we have PV, T, and N, this is going to be the ideal gas law, which is PV equals nRT. Since we're solving for pressure, so technically P equals nRT over V. Number 22, which gas law must be used to solve the problem? We are given an initial volume, an initial temperature, a final temperature, and it's asking for the final volume. So since we are dealing with volume and temperature, this is going to be Charles' law, V1 over T1 equals V2 over T2. It's asking for the final volume, so our equation for solving for actual V2 would be V1 T2 over T1. Number 23 gives you an initial and final pressure, an initial and final temperature, and then it gives you an initial volume asking for the final volume. So since we have all three of those variables, it will be the combined gas law, P1 V1 over T1 equals P2 V2 over T2. Since we are solving in this situation for the new volume, it would be V2 equals P1 V1 T2 over everything left, which is P2 T1. Then the final one, it gives you an initial and final volume, and then an initial pressure asking for the new pressure. So we're solving for P2. Since we have pressure and volume, that's going to be Boyle's law, P1 V1 equals P2 V2. Since we were solving for P2, our equation specifically for that would be P1 V1 over V2. And I hope that all helps you study for your Chapter 12 test. If you have any questions, please let me know. I hope you have a great day.